So what we're looking at here is ionic nomenclature and formula writing with polyatomic ions. So what do I mean by polyatomic ions? I mean these ions that are from the ions list that you guys have been memorizing. So carbonate, acetate, nitrate, phosphate, etc. So basically, as you guys should be familiar with, ions that are polyatomic ions are obviously ions that have multiple different atom types. Notice carbon and oxygen are the ones present in the carbonate ion. Most of the anions, or most of the polyatomic ions that you've been memorizing are anions. One of the most common positively charged polyatomic ion is the ammonium ion. Okay, so you'll come across that as well. So how do we go about naming ionic compounds that contain polyatomic ions, and how do we write formulas, etc.? Okay, well, basically you follow the exact same rules as the monoatomic ion naming that you've been doing up until now. The only difference is that you do not create an IDE ending. So if we look at the example down here, we can see that we have a ionic compound. First of all, we have a metal. Okay, and obviously we have a group of nonmetals here. The fact that I have that group of nonmetals implies to me that that's probably a polyatomic ion. Okay, and because I've memorized my ions list, okay, I know that that's going to be a carbonate ion. So how do I go about naming this? Okay, well, just like I would with the normal, the monatomic ion naming setup. Okay, I name the positively charged cation first, which in this case is sodium. Okay. Carbonate is the name of this polyatomic ion, so sodium carbonate. Okay, there's no IDE ending. We just name it with the polyatomic names of that ion. So it's really straightforward in that sense. Now, how do I go from name to formula? Okay, so let's go ahead and let's look at that. So if I did this sodium carbonate example, okay, remember I'm going to be using the cross down method. So sodium has a +1 charge. We know that carbonate has a 2- charge. Now, how do I treat these? Normally, the approach that I take here with the polyatomic is that anytime I'm crossing down the charges, I put parentheses around the ion itself. Okay, so what I'll do here is I'll actually place parentheses here. Why? Because carbonate ions always have 1 carbon and 3 oxygens. The charge here is the only thing that I'm crossing down. Okay, so what I'm going to do is I'm going to have Na. Okay, the 2 is going to come down here because I'm crossing this down. The 1 is going to, excuse me, come down here because I'm crossing the +1 down. So when I go ahead and put this into my formula, okay, I'm going to have this. Now, notice this 1 here on the outside of these parentheses is a redundancy. So these parentheses also happen to be a redundancy. There's no reduction in the charges, so I can just write this very simply as Na2CO3. Okay. Now, if I needed more carbonates in order to balance out the charge on the sodium, I would keep the parentheses, and obviously this number would be larger than 1. Okay, so it's a very simple setup in terms of naming and formula writing. It's the same type of rules that we've been using with the regular monoatomic ions, but in this case, when we're going from formula to name, we do not add an IDE ending. It's just the ending name, or it's just the name of the polyatomic ion. Okay, and when we're crossing down, it's good bookkeeping to utilize parentheses initially, and then if necessary, keep them, and if not necessary, like the example we see here, we go ahead and drop them. Okay, let's do a couple of practice problems here. Okay, once again, guys, we have a metal, and we have this polyatomic ion. Okay, so notice though that this is a transition metal. Remember that the nomenclature approach is going to be exactly the same as we have been doing. In this case, we have to account for the fact that we have a transition metal, so we know we're going to have parentheses. Okay, so iron is Fe. All right, iron something. Okay, this polyatomic ion is carbonate. Okay, so iron something carbonate, right? Okay, well, we have to figure out what the charge on iron is, excuse me. Okay, we know that carbonate is a CO3 2- ion. I have one carbonate ion, right, for every one iron, right? So in order to balance out the -2 here on this single carbonate, I have to have a +2 on my iron. So my parentheses are going to have the Roman numeral 2. So iron 2 carbonate is how we're going to name this compound. Okay, if we look at this next example, we have strontium, okay, as our metal. It is a main group metal, normally has a +2 charge, so because of that, we don't account for any of the multiple quote-unquote oxidation states that would be present in a transition metal. Okay, so nitrate is the name of our polyatomic. So strontium nitrate is going to be our name. This is just a straightforward approach. There's no need for parentheses because it's not a transition metal. And this is the nomenclature approach that you would take. Okay, and this is the last example. We're once again looking at a main group metal, so we're not going to need any parentheses. Potassium is the cation name that we're going to be using. Okay, and this polyatomic is chlorite. Okay, so very simply, we have potassium chlorite here. So this is the way we're going to go from formula to name when naming with polyatomic ions. Remember, guys, there is no changing of the ending, right? We just use the name of the polyatomic ion in order to properly complete our ionic nomenclature with polyatomic ions. Other than that, we follow all the other rules that we've been using in other ionic naming basics. Basically, we're making sure, that we include our charge when it's a transition metal, and that we are approaching each question with the cation being named first. Okay, so let's go ahead and let's look at these examples of polyatomic ion formula writing. So we were looking at naming from formulas earlier. Now we're going to go the opposite direction. Okay, so we're going to be following the same set of rules we have been. The only difference here is that we want to make sure that we're utilizing parentheses to help us track the appropriate subscripts. Okay, so in the example I have here, I have copper +2. I know that because the Roman numeral 2 is in these parentheses, which corresponds to the transition metal's charge. Acetate is one of the polyatomics that we should have memorized. So C2H3O2 -1. Okay, I'm going to put parentheses around this, around the ion, the polyatomic ion, because I want to make sure that I don't accidentally incorrectly write some of the subscripts. Okay, so what I'm going to do is I'm going to cross down. Okay, so Cu, right, 1, C2H3O2, 2. Okay, so this is the way I would write this. This makes sense. Why? Because this copper has a +2 charge. Each one of these acetate ions has a -1 charge, so I need 2 of those in order to balance the +2 that's here. Now, if I didn't use the parentheses, look at what could have happened. We could have ended up with Cu, C2H3O22. Okay, without this parenthesis set that you see right here, there's potentially the possibility of creating a quote-unquote new formula. Obviously, C2H3O22 is not acetate. Okay, so the parentheses allow us to delineate the difference between the number of polyatomic ions and the number of atoms in the polyatomic ion. So it's a bookkeeping method that helps us not make any silly mistakes that'll cause headaches later down the line. So let's go ahead and let's move on to the next example. Okay, so chromium +3 is what I have here. Sulfite is going to be SO3 2- from that chart. Once again, I'll put parentheses around my polyatomic ion formula, excluding the charge. I'm going to cross down those ions. Okay, and this is going to give me Cr2, parenthesis, SO3, 3. Okay, the subscripts can't be reduced any further. The overall charges make sense. Okay, and this gives us our formula for chromium sulfite. Okay, and lastly, let's go ahead and let's look at this magnesium hydroxide formula. Okay, so magnesium, we know from the periodic table, +2. Hydroxide is a negatively 1 charged polyatomic. And put those parentheses around that polyatomic. Okay, cross down. This is going to give me MgOH2. Okay, that can't be reduced down any, so this is our appropriate formula. So basically, when we're going from name to formula, you guys want to make sure you're using the parentheses in order to not make any errors like we saw in this first example. Okay, you want to make sure that you're checking and seeing if the charges the subscripts can be reduced. And other than that, these are the examples.